Welcome to The Explainer. All right, today we're going to dive deep into Streptococcus acidominus, a bacterium that honestly demands a second look from every single one of us in the clinical lab. We've pulled this entire review together using a comprehensive Gemini deep search, and for all of you who want to go straight to the source material, everything is available in the linked notebook. For the longest time, this was just considered a veterinary microbe, something you'd expect to find in cattle. But as this quote from the literature makes crystal clear, that view is completely outdated. We're now looking at this organism in a whole new light as a really significant and sometimes life-threatening pathogen in human medicine. So we're going to tackle this just like a clinical case file. First, we'll get into why this bug is suddenly on our radar. Then we'll head to the bench and walk through how to actually identify it. After that, we'll look at the real-world diseases it causes, and finally, we'll get to the most critical part. How do we treat it, and how do we prevent it? Okay, let's get right into it. Section 1, the emergence. The big question is, how on earth did a bacterium that we mainly associated with animals make this jump to become a genuine clinical problem for us? This timeline really tells the whole story. Its so-called emergence isn't really about the bug changing, it's about our ability to see it changing. For decades, it was probably just getting misidentified or lumped in with the rest of the viridans group strep. But now, with technologies like MALDI-TOF MS becoming routine, we've basically unmasked a threat that was hiding in plain sight all along. And its formal classification, this is really important. Placing it squarely within the viridans group Streptococci isn't just a trivial label. It immediately tells us what to expect, that it's going to share a lot of characteristics with other alpha hemolytic strep, and that sets the entire stage for how we approach its diagnosis. All right, let's move into the lab and break down how we can reliably nail down an ID for this organism. We're going to go from the absolute basics at the microscope right up to the advanced molecular methods that are so critical in a modern lab. So, of course, the whole investigation kicks off at the microscope. Under the gram stain, you see exactly what you'd expect from a Strep aureus, those classic gram-positive cocci, forming pairs and chains. This is step 1, our first big clue pointing us in the right direction. Now, when you get this on a plate, there are a few key things you're looking for. The most telling sign is that unmistakable alpha hemolysis, that partial greenish clearing on the blood agar. And because it's capnophilic, it really prefers a CO2-enriched atmosphere to grow well. Seeing those small, shiny colonies with that alpha hemolysis, that's how you start building a really strong presumptive ID. So this is the big one, right? How do we differentiate it from its notorious and much more common relative, Streptococcus pneumoniae? I mean, they're both alpha hemolytic. Well, the answer lies in these classic bench tests. Streptococcus acidominimus is resistant to optocline, and it's not soluble in bile. These two simple fundamental tests are absolutely crucial. And this slide just perfectly illustrates the modern challenge we face. On one hand, you have MALDI-TOF, which is incredibly fast, we're talking minutes, but its accuracy is only as good as its database, which can sometimes struggle to tell these closely related viridans species apart. On the other hand, you have 16S ribosomal RNA gene sequencing, the gold standard for accuracy, but even it can sometimes lack the resolution to differentiate at the species level. It just reinforces that for critical isolates, you really need a multi-pronged, polyphasic approach. Okay, so we've confidently identified it in the lab. What does that actually mean for the patient? Let's switch gears and look at the real-world clinical impact and the spectrum of disease this organism is responsible for. The range of diseases is surprisingly broad and serious. It is so important to understand this is not just some bystander or contaminant. The literature is full of cases where Streptococcus acidominimus causes severe invasive disease, everything from life-threatening infective endocarditis to deep-seated brain abscesses. And when you look at the case reports, a really consistent pattern emerges. Streptococcus acidominimus is a classic opportunist. It's not typically infecting healthy people out in the community. No, it primarily hits our most vulnerable, hospitalized patients, the ones who are post-op, immunocompromised, or have central lines and other devices. And that brings us to the most critical question for clinicians, and frankly, a key responsibility for us in the lab. How in the world do we effectively treat these infections? So the number one takeaway here is that you cannot guess the antibiogram. The resistance profile is all over the map. We've seen resistance to penicillin, erythromycin, and especially high rates of clindamycin resistance. There are even multi-drug resistant strains out there. This makes antimicrobial susceptibility testing non-negotiable.
it is absolutely mandatory. For now, at least, vancomycin seems to be holding strong. Now, for the most serious infection, endocarditis, everything hinges on this one number. According to EUCAST, the European Committee on Antimicrobial Susceptibility Testing, a penicillin MIC, or minimum inhibitory concentration, of 0.125 milligrams per liter or less is what defines high-level susceptibility. This single value drives the entire treatment decision tree. So let's look at a really practical example. The Dutch Working Party on Antibiotic Policy, which is known as SWAB, gives us an excellent, super clear framework for treatment that is stratified based on that exact MIC value we were just talking about. And you can see just how logical this is. The treatment gets more intense as the MIC goes up. For those really susceptible isolates on a native valve, 4 weeks of a single drug is enough. But once that MIC starts to creep up, you have to add gentamicin to the mix. And of course, for any infection involving a prosthetic valve, you're automatically looking at a longer duration, a minimum of 6 weeks. Now, these principles are pretty similar across international guidelines, but, and this is a big one, it's absolutely crucial to note the differences when you're treating kids. The AHA pediatric guidelines explicitly say to avoid the 2-week short course therapy that is sometimes an option for adults. They much prefer a full 4-week course of a single drug for susceptible strains to avoid the risk of immunoglycoside toxicity. Okay, finally, let's zoom out and look at this from a public health and hospital perspective. How do we stop these opportunistic infections from even starting? The prevention strategy here is really multi-layered and very targeted. It all starts with the basics, universal standard precautions, especially meticulous hand hygiene. For patients with respiratory infections, you add droplet precautions. But then it gets highly specific with antibiotic prophylaxis only for the absolute highest risk cardiac patients, and fluoroquinolone prophylaxis considered for high-risk neutropenic patients. You know, our understanding of pathogens like Streptococcus acidominimus is constantly evolving. And honestly, the real-world data from labs just like yours is invaluable. So if you found this useful, please subscribe to the channel. We'd also love for you to share your feedback or any interesting case experiences you've had in the comments. Let's build our collective knowledge together. And we'll leave you with this final thought. The story of Streptococcus acidominimus is the perfect example of how better technology can reveal a hidden threat. It really makes you wonder, right? As our diagnostic tools get even more powerful, what other clinically important pathogens are still out there, just hiding in plain sight within these broad, undifferentiated microbial groups?